Hi everyone, welcome to our lesson on proofs. This is the last part of our chapter on further algebra, so well done for all your hard work so far. And let's finish this on a positive note. Okay, so first we're going to look at how we communicate proofs, but before we do that, I'd really like you to try these questions. They're fairly straightforward. The first one's about sequences, so make sure you substitute so that you can answer these questions, whether 1, 2, or 3 applies. For question 2, you're just expanding and simplifying. And then for question 3, I need you to tell me if they're equations or identities. Okay, so pause, have a go, and then we'll go through the answers together. Okay, well done. Let's just get this set up for you. Okay, light's already on. Let's make sure it's focused enough. That seems focused enough. Okay, lovely. All right, so for question 1, they're asking you which sequences contain only even numbers, only odd numbers, or even and odd numbers. Well, if we look at part A, they've told you it's n plus 2. Oops, sorry. Okay, and let's say I let n equal 1. So for the first term, well, then I would get 1 plus 2, which is equal to 3, and we know that that's odd. Okay, if I let n equal to 2, then I would get 2 plus 2, which is 4, which we know is even. So we can confidently say that part 3 would apply to this first sequence. For part B, we have 2n. Okay, so if we let n equal 1, then we would get 2 times 1, which is 2. And if we let n equal 2, then we would get 2 times 2, which is 4. And it doesn't matter what n equals, because if we multiply it by 2, we know it's divisible by 2, which means it will be an even number. So our answer to this one would be that it was only even. For part C, we have 5n. Okay, so let's have a think. If I do 5 times 1, okay, when I let n equal 1, then we get 5 times 1, which of course is 5. Okay, and if I let n equal 2, then I get 5 times 2, which is 10. And if we look, that's odd, that's even, so we would again pick part 3. Okay, and for part D, we have 2n minus 1. Okay, so let's let n equal 1, and that's going to give us 2 times 1 minus 1, which is 1. If I let n equal 2, then I get 2 times 2 minus 1, which equals 3. And actually, if I continued this pattern, I would always get an odd number. Okay, so we can say that this is part 2 is correct. They're always odd. And finally, section E says that we have n squared. Okay, so if we let n equal 1, well, that's going to be 1 squared, which is equal to 1. Okay, and then if I let n equal 2, then I'm going to get 2 squared, which is 4, and therefore it could be both. Okay, so all this question was really asking you to do was to substitute in your term numbers so that you can get your term values and then decide which category it belonged to. Okay. Right, so question 2, we were meant to be expanding. So x times x minus 1 is going to be x squared minus x. Can't simplify that any further. Okay. Part B, we have x plus 3 squared. We've done tons of these, so that's x squared, and then plus the 6x, and then plus the 9. Please feel free to write that out so that you can see that. 3x gives us 6x, 3 times 3 is 9. Okay. Part C, we have 2x times 2x plus 1. Okay, it's just linear expanding, so 2x times 2x is 2x. Sorry, what am I saying? 2x times 2x is 4x squared. Okay, and 2x times 1 is plus 2x. Apologies. All right, so that one's done. Can't simplify any further. None of them are like terms. Question 3, we now are being asked if these are identities. Now, in order for something to be an identity, the left-hand side has to equal the right-hand side. So let's take a look at the first one, part A. The left-hand side is 2 times n plus 3. And if I expand that, I get 2n plus 6, which is equal to the right-hand side. And since that's the case, I can say that 2n plus the 3 is equal to always 2n plus 6. And we use the 3 lines when it's an identity. Okay, so that is an identity. Right. Part B. Okay, we have 5n minus 7 is equal to 8. Well, who says 5n minus 7 is always equal to 8? That's not an identity, so that's an equation. Okay, and part C, we have a half times 4n plus 10 is equal to 2n plus 5. So let's work on this and make sure it is actually equal to that. So our left-hand side is equal to a half times 4n plus 10. Okay, that is equal to 2n. And then plus 5, which is equal to the right-hand side. So that is an identity, okay? And we can say that a half times the 4n plus 10 is always equal to the 2n plus 5. All right? Right, with one more of those. So 2 brackets 3n minus 5 is equal to 4. Again, I'm not going to make that equal to a 4 because there's an n involved, and so that is an equation, not an identity. Okay, so hopefully that makes sense to you guys. We would obviously then be able to solve both of the B and D, but they didn't ask us to, so we're not going to bother. Right. So let's move to the first type of proof question we're going to be dealing with, okay? And that is where we're communicating a proof through showing that something is the case. The nice thing about these questions is that when you get to the stage where you've shown it, you know that you're correct. All right. Usually we have to refer to the left-hand side and the right-hand side. We use LHS for the left-hand side, and we use RHS for the right-hand side. Okay, so let's just show this to you so that you can see it a little bit better. So to show that a statement is an identity, we expand and simplify the expressions on one or both sides of the equal sign until the two expressions are the same. Okay, so in this case, it says show that x plus 4 squared minus 7 is always equal to x squared plus 8x plus 9. So we would make sure we expanded and we simplified the left-hand side as they did, and then we would state that they were equal to each other and therefore they're always equal to each other. Okay, and that's how we do this. So if you could press pause and make sure that that's in your notes, that would be lovely, and then press play once you've done that. Okay, good, thank you. Right, so I would like you to show that all of these are identities, okay? Exactly as we just did in that model question. So pause it, okay? Try the questions, make sure they work out. Remember, you can start with the left or you can start with the right as long as you get to them both being the same, okay? And yeah, press pause, have a go, and then press play when you're ready to make sure you got the answers correct. Okay, well done. That should be enough time. Right, so let's try these together. Right, so here we have x minus 3 squared plus 6x, and that is the left-hand side. Okay, that's the one I'm going to choose to expand. So that is equal to x minus 3 times x minus 3 plus 6x, which we know is x squared minus 6x plus 9 plus 6x. Those cancel. Okay, and that gives us x squared plus 9, which we know is equal to the right-hand side, and therefore we can state that x minus 3 squared plus 6x is indeed always equal to x squared plus 9, and that is an identity, and we've shown it. So that's finished. Okay, so well done those of you who got that. Part B, we have x squared plus 8x plus 49 is equal to the left-hand side. I'm not going to change that one because I don't need to expand it, so let's do the right-hand side, which is x plus 7 squared minus 6x, okay? Let's work on that one. So that's equal to x plus 7 times another x plus 7 minus 6x. That's going to give me x squared plus 14x plus 49 minus 6x. And that gives me x squared plus 8x plus 49, which is equal to the left-hand side. Okay, and just make sure you state that so you're very, very clear. And we can now say that therefore x squared plus 8x plus 49 is always equal to our x plus 7 squared minus 6x. And that one's finished. Okay, part C, we have x minus 5 squared minus 4 is always equal to x minus 3 times x minus 7. Okay, so choose, unfortunately for this one, we kind of have to work on both to get them to be similar. So let's start with the left-hand side. Okay, so the left-hand side is equal to x minus 5 squared minus 4. That is equal to x minus 5 times x minus 5 minus 4, which is x squared minus 10x plus 25 minus 4, which gives us x squared minus 10x and then plus 21. Okay, at this stage, you now want to work on the right-hand side separately. So that's going to be x minus 3 times x minus 7, which is x squared minus 3x minus 7x is minus 10x, and then minus 3 times minus 7 is plus 21, which we can now say is equal to the left-hand side, okay, because they match, and we can now state that therefore x minus 5 squared minus 4 is indeed always equal to x minus 3 times x minus 7. So that is an identity. Okay, last one of those. There we go. Okay, so we have 16 minus x plus 2 squared is supposed to be always equal to 6 plus x and 2 minus x. Right, so let's start with one side. So we're going to start with the left-hand side. I'm going to put that in a square bracket though, because obviously we're going to end up taking away all of it once we've expanded. Okay, so that's 16 minus x plus 2 times another x plus 2, which gives me 16 minus, in a square bracket, x squared plus 4x plus 4, square bracket, which equals 16 minus x squared, now don't forget to distribute to all, minus 4x, and then minus 4. Okay, we can simplify a bit. That leads to negative x squared minus 4x, and then 16 take away 4 is plus 12. So we've done the left-hand side. Now we need to do the right-hand side. Okay, so I'll do this the long way. 6 times 2 is 12, plus x times 2, which is 2x. 6 times minus x, which is minus 6x, okay, and x times minus x, which is minus x squared. Right, so have I done something silly? Let's just check, because it doesn't look, yeah, no, it should match, there we go. So we've got 12 minus 4x minus x squared. I'm going to rewrite this out so it looks the same. Minus x squared minus 4x plus 12, which is equal to the left-hand side. So now we can state that therefore 16 minus x plus 2 squared is always equal to 6 plus x times 2 minus x. Okay? It says for part C, can you think of a different method than the one given in the hint? And the hint said first expand and simplify the left-hand side, then factorize. No, there is a different method. The one that we did was to actually expand both and simplify, which is perfectly fine as well. Okay? Okay, so the other type of communication question we need for proofs, okay, is where we're maybe incorporating a little bit of algebra, okay? So let's make that full screen for you. I'd like you to try both of those questions. So press pause, see if you can apply the learning we've had in terms of how we show things. Make sure you're very clear with your steps. If they say to show something, they want to see every step. Okay, all right, so pause, have a go, and then we'll go through them. Okay, well done. Let's take a look. There we go. Right. Okay, so let's look at question 5 first. So this is a communication question. So let's see. It says to show that x minus 1 times x plus 1 is always equal to x squared minus 1. So we start with the left-hand side, and we would have that that's x minus 1 times x plus 1, which equals, don't need a bracket, x squared plus x minus 1. Those cancel, and that does indeed give us x squared minus 1, which is equal to the right-hand side. So now we can say, therefore, x minus 1 times x plus 1 is indeed always equal to x squared minus 1. Okay, so that is an identity, and we've shown it. Part B, part I first, says use your rule to work out 99 times 101. Well, that's interesting. So let's take a look at this kind of concept of x minus 1 and x plus 1. Well, if that's the 99, and if that's the 101, then what must x be? X must be equal to 100. So now I could say that 99 times 101 is actually going to be equal to 100 squared, take away 1. Because my x value we know is 100, and apparently this is equal to x squared minus 1. 100 squared is x is the 100 squared minus 1. Okay, which is going to be minus 1, which is going to be that. Okay, right, and then part 2 says to use it to work out 199 times 201. Okay, so in this case, again, we're looking at this relationship, and we know that our numbers are 199 times 201, so the x must be equal to 200. Okay, so this is going to be equal to 200 squared minus 1. Okay, so okay, and that's equal to 3, 9, 9, 9, and another 9. Okay, lovely. All right, so we've shown that, and we've actually applied it to another situation. Okay, so please make sure you actually look at what something means in terms of a pattern so that you can apply it to a new situation. All right, so in question 6, we now have 2 rectangles. I can see they're probably going to be working with area and cutting something out. I don't really have to think too hard to figure that out, so make sure you do look at a diagram before you read the question. All right, it then says that the blue card is a rectangle of length x plus 5 and width x plus 2. That's already in the diagram. Part A is to write an expression for the area of the blue card. Okay, well that's fine. Well, that's going to be area. The expression will be x plus 5 times x plus 2, so that's done. Then it says a rectangle of length x plus 1 and width x is cut out and is to be removed. It says write an expression for the area of the rectangle that gets cut out. Well, again, we're going to know that the area is going to be x times the x plus 1, length times width. Okay, done. And part C says show that the area of the remaining card is 6x plus 10. So we're going to have to do that area minus that area. So that's going to be x plus 5 and x plus 2 minus our x times x plus 1. But please remember to put that in a square bracket like I've taught you. We don't want to make mistakes with our negatives. So this is going to give us x squared plus 5x plus 2x plus 10 minus x squared plus x. That actually becomes x squared plus 7x plus 10 minus the x squared, because that distributes, and also to there, minus x. Those cancel. Okay, and we get 7x minus x, which is 6x, and then plus the 10. And we've shown it. Okay, so done. Therefore, the area of the remaining card is 6x plus 10. It is a very good idea when you have proof questions to write a sentence at the end, making sure you're very clear in your communication, okay? Because you don't want to lose that mark. Right, so let's see if you're ready for an exam style question. I'm going to make that bigger for you now. Okay, you're going to pause and you're going to have a go. Okay, so let's see how we did. Hopefully we got 3 marks. Let's take a look. Okay, so in this particular question, they're saying to us that the diagram shows a large rectangle of length 3x plus 4 and width x, and a smaller rectangle of length x and width 5 centimeters is cut out and removed. Fine. The area of the shape that is left is 70 centimeters squared. Show that 3x squared minus x minus 70 equals 0. Okay, so this is very similar to the previous question, except this is now an exam style question. So you're not going to get the parts A, B, and C that we had in the previous question. You're going to have to know to do that. Well, if I want to talk about the area of the remaining shape, I'm going to have to find an expression for the area of the remaining shape. So what we're going to do is we're going to start with the large rectangle area, and you would label this in your exam so that the examiner was really clear about what you were doing, is going to be x times our 3x plus 4. Okay, and then you would expand that. That's 3x squared plus 4x. Okay, then you would do the small rectangle area. Okay, which we know is going to be 5x, because it's just 5 times x. That's done. And then you would have to do the remaining area. Okay, so it's not very hard to write this out and be very, very clear with what you're doing. And that's going to be 3x squared plus 4x minus the 5x, which is equal to 3x squared minus x. So that is the remaining area. But we know that we need to let the remaining area equal 70, because that's what they told us it was. So that means that 3x squared minus x will be equal to 70, and therefore, if we take away 70 from both sides, we get 3x squared minus x minus 70 is equal to 0. And that's exactly what they wanted you to show. Now I've put a therefore in front of that. That's what that means. And I said I'm finished, so that would be enough for showing this particular answer. Okay? Right, so just as a little taster for when we move to the second lesson related to this, okay, I want you to have a go at this question. I'm going to make it full screen for you and make sure we talk about it before we finish this lesson, okay? So press pause, see if you can get this, and come up with the counter examples, okay? Okay, good. Hopefully that was enough time. Let's take a look. Not that I need to give you time on that because you can pause the video, but that's okay. Right, let's begin. Question 8, part A, says to give a counterexample to prove that these statements are not true. All prime numbers are odd. Well, no. 2 is even and prime. That's always your answer to that question. That's the one that disproves it. Part B. The cube of a number is always greater than its square. Well, that's not true. 1 squared is equal to 1 cubed, which is equal to 1. So there's your counterexample there. Part C. The difference between two numbers is always less than their sum. Well, that's assuming that the numbers aren't negative. Yes? So if I added 1 and negative 2, I would get negative 1. But if I did 1 take away negative 2, I would get 3. So that would be your counterexample. They haven't considered negative numbers. Okay. And for part D, the difference between two square numbers is always odd. Between two square numbers. Well, let's take a look. Okay. Well, what if I have 2 squared is equal to 4? That's even. And 8 squared is equal to 64. Well, that's interesting. 64 minus 4 is equal to 60, and that's even. So they're wrong. It is not always odd. Okay? So you may have questions that ask for counterexamples so that you can disprove something. All right. Next lesson, we're going to be looking at a different type of proof, okay, which involves generalizations. And what I mean by that is we're going to have to generalize what odd numbers are, what even numbers are, how they work together, and apply that to a little bit of algebraic proof as well. Okay, so we're going to stop there today because now I've taught you to show your work and how to show your proofs, and next time we will be looking at how we actually conduct proofs where we need a little bit of background information in order to do that. Okay, all right, so well done today and looking forward to the next one. Take care.